This talk about a new axiom set for two-dimensional Euclidean geometry here, and this is the subtitle, Fruit of Reinventing the Wheel. And if you know the history, a lot of people have tried that and failed. I hope I'm not one of them again, right? So the first thing is why I want to do that, because I'm a father and I have a daughter who happen to go to high school courses on geometry. Well, the first thing, I will claim, sorry to insult the teacher here, US math education later math logic, for example, for the geometry as an example, right? The first problem is the lack of time, right? When I look at US geometry, how much they cover in 1 year. In the high school, the first year, they cover plain two-dimensional Euclidean geometry, three-dimensional Euclidean geometry, analytic geometry, and some of the trigonometry, right? That's too much in 1 year. Let me tell you how much I spent time in China for this, right? I spent 4 years on plain Euclidean geometry. 4 years, that's in middle school. 1 year in high school, that's for solid, three-dimensional Euclidean geometry. And in the parallel, I spent 2 years on analytic geometry and 2 years on trigonometry, right? There is a value to do that because the problem I see here is, when I learned the Euclidean geometry, we prove one theorem at a time, right? We reach everything has to be proved, right? There's no jump, right? But in here, when I see how my daughters study Euclidean geometry, they are spoon-fed with the content of the theorem. Okay, this is a triangle in equation, right? But what's the cause, right?
Yeah.
But if you think about it, the whole essence of mathematics is logic, and the whole essence of geometry, Euclidean geometry, is proof, right? In fact, I think the United States is lagging behind. Even the United States spend a lot of money on math education, but this is something lacks. And in fact, I feel very disturbing because sometimes when I see their homework, they have certain homework, apply this equation, calculate this. There are certain optional homework, prove things, right? Geometry is proof, right? Without proof, the formula is useless, right? That's called logic. So basically, what I see in the United States is knowledge. The math education as a whole is knowledge. It's called, this is the fact that I remember this. It's not about thinking, right? That's the problem. And also another problem is their exam, right? All the standard tests, I look at it, it's all multi-choice, twice. But that's wrong, because when you look at the geometry, that's a thinking process, right? In China, what we do here, step 1, step 2, step 3, right? Teacher grade based on which step, and they tell you which step you make a mistake. That's how the exam should be, not in this country, unfortunately. And
you finished, sir? You finished?
No.
Sorry. Sorry. All right.
Yeah. So the next thing is, I'm thinking about maybe my daughter can read some textbooks. But when I look at textbooks, they are too perfect, right? They say, okay, there are, everything's perfect. But when you think about it, the thinking not come from perfect, but from imperfection. When you make mistakes, when you find, something you don't understand, right? But all the textbook does not cover that part. And the final thing is, United States, the calculation again is knowledge, right? It doesn't teach students how to ask the question, but I think that's the most important. So how about we are disappointed with normal education? How about AP, right? AP unfortunately is run on the same course, right? They rush things to students, right? Even the college things to students without sufficient discussion and understanding, right? So how about?
I'm sorry. What is AP?
Advanced placement.
Advanced placement.
Advanced
placement.
Basically, what they do is that they try to help the student to apply for college. They dump college course into high school, right? That's basically AP is. Nothing new about it. Talk about math competition and private tutoring. In my opinion, they are skills, not thinking itself, right? in fact, if you look at around in my neighborhood, there are street malls which has A plus math class there, this kind of thing. So this is, they all teach you skill, not, train you to answer questions. So let me continue a little bit. I think what left out in today's math education is thinking, right? Let me say what kind of thinking I'm thinking about, right? The first one is dependent thinking. That means you learn some skill from one area, apply to another, right? Right now, maybe, I don't know how much percentage of graduate would use that. Another one is called critical thinking. Critical thinking is used very much in industry, right? You have to make sure every math, every analytics, everything has to work. But in my opinion, it's not used enough in education, right? You don't teach students try to figure out what's wrong with certain things. And also, there's something called alternative thinking, right? And if do you have some alternative solution for certain things? Here, I have to thank my geometry teacher very much in my high school. Basically, his requirements for each geometry, two-dimensional Euclidean geometry, not only have to find one way to prove it, you have to find a different way to prove it, right? Probably I spend threefold amount of time or fourfold amount of time, right? But it's very interesting, and it's actually make me to love the geometry so much because that's the beauty of logic, right? And also there are some things called creative thinking, which always there's a lot of institution here about creative thinking, something. It's always associated with imagination, right? But I don't want to go to this subject. In fact, I think there's another thinking which is very important called first thought. That means your virgin thought when you faced with a new problem, right? How do you think about it? I think that is come naturally, but unfortunately in today's spoon-feeding education, that's get lost very easily, right? People don't have a chance even to consider this for a while. So let me say something about my ideal education. What ideal education should be, the purpose of education is not to teach students how to answer a question, but how to ask a question. That's the most important part, right? But I think that's completely lacking in today's education in the United States. In fact, it's also lacking in China now because they try to adopt the United States model, try to spoon-feed the student all the time. In fact, the other day I looked at their high school entrance exam. Frankly, it's at the difficult level of my second grade in college, right? They just do too much, I think. And so basically, I basically think we should think about one thing. We should think about, before you give a solution to a student, a new subject, maybe you should ask them to think, right? You basically not be afraid of trying to reinvent the wheel, right? The mentality here is if you create a solution, if you by yourself, you create some solution, you created solution worse, you will learn something from standard answer. If you create a solution is better, you will invent something, right? So for this purpose, I will use Euclidean geometry as a, in fact, this paper is the combination of my other thinking and the first thought of my daughter Alice, right? So basically, she started to read about Euclidean geometry, started to ask me some question, and suddenly give me a light bulb just right out. Maybe there's something wrong in the conventional approach, right? My background, as I said, I'm an experimental physicist, right? So my approach is a little bit different from the mathematician. The first thing is, the question is, mathematics science or art? And here's something I noticed first day when I become registered for graduate study in University of Sternberg. And the university is organized by colleges, and it's kind of interesting. There are College of Medicine, there are in their Department of Internal Medicine, Department of Radiology. There's a lot of departments. I know the meaning, but I don't know the pronunciation, right? And there are College of Liberal Art, German study, social study, that's fine, right? There are College of Engineer, Mechanical Engineer, Electrical Engineer, very clear what they are doing. But there's one odd one, it's called College of Arts and Science. Well, there are departments which are clearly arts, like music, drama, painting, right? Clear art. There are departments of very, clearly science, like physics, biology, chemistry, right? And but when you look at the student at the registration, they are quite different. There are one group which has a high percentage of female, and they are very stylish, or in some cases very anti-stylish. They are generally handsome, beautiful, in some cases ugly, but still very impressive. And of course, they are art students, right? There are another group which is plain, common, nerdy, right? That's a science student. But how would the university combine a group, two different group of people from two different departments, create a college of art and science? I was told later because the university cannot decide on which side the department of mathematics should belong to. Okay, all right. So I will start my methodologies as experimental physics. First, I will do observation. From the observation, I need to generalize our observation into axiom or definitions, right? Once we have axiom definition, we use a mathematical logic to come up with theorems. The final step is I need to do application. The first thing is a reality check. I have very fortunately for us, Euclidean geometry is very observable in 2 dimensions, 3 dimensions, right? For 2 dimensions, it's very observable. So we can say if our axiom come out really makes sense or not in reality. That's called reality check. In fact, reality check separate the science and art. If you have a subject which can do reality check, that's probably science. On the other hand, you have a subject, you will standard if it's beautiful or not. In the case of modern art, if it's ugly or not, you will say that's art, right? So using this standard, you will say part of the Department of Mathematics are art, and part of Department of Physics are art, like string theory in physics. Right now it's still art because there's no reality check. And after that, when you have the reality check, you can say, do some tests to say whether the space we live in is flat or not, is Euclidean or not, basically. So, but still, the waterproof detection is very important, no matter what. I will give you an example in my talk. And now, let's apply this experimental approach in Euclidean geometry. Euclidean geometry, as we all know, just originally is for flat plane because the two tools they are using, handheld and the ruler, only work on flat plane, right? Doesn't work in perfect plane. And now the natural question is, okay, you say this is the geometry for flat plane. How do you define flat plane? There's, you can describe it, but then certainly you're out of the word because you cannot describe it. And in fact, that's a experimental physics. My question is, what's the way you can destroy it, right? So suppose I have a very flat piece of paper, right? That's represent the flat plane. I can bend it. That's one way I destroy it. I can fold it. That's another way I destroy it. And I can make a hole in it, right? I can say, because Euclidean geometry is infinitely large flat plane, I can say, okay, here is a limit, has a bound, right? I can stretch it, right? Stretch, and then can cut and switch, right? Say I can do this, make a cone from it, right? Cut and switch. So when we do this experiment, we find, okay, this operation will create so many objects between us. How would you study it, right? The way to simplify it is called abstraction, right? Let me put some limit on it. For example, if I look at all the distraction I made on the flat plane versus the original flat plane, I immediately notice one important difference. My flat plane, every point is in the exact same neighborhood, it's uniform, right? If I fold it, there are two directions, right? This direction and that direction are different, right? Or if I do anything else, I will create something special, right? The only difference is if I stretch it uniform, I go from here to here, right? A ball. Every point on a ball is in a uniform place. It's in exactly the same neighborhood. You cannot tell the difference, where it's from, right? So if assuming I have a way to detect what's special, if a point in a special place, assuming, that's a big assumption. If I assume uniformity, then my problem reduced to compare a ball to a flat plane, right? That's become much more manageable, right? Just this is how abstraction, right? We just abstract something without the ability to prove that. Then the goal of this, as a quantum physicist, is I want to come up with certain observable, what thing we can observe as a general rule, and something measurable, we can always measure as a general rule. Then, after we do the abstraction, we still have to, as an experimental mind, we have to go back, try to do the reality test. So testability is a true requirement in physics, right? You do some theory which is not testable, not very useful. So from this point of view, so basically, can infinity be tested? Well, infinity can only be tested one way, right? You can only prove a value which is not infinity, but you cannot prove it's infinity. Let me give you an example, right? We say Mr. Magellan and his crew is very brave. You try to prove the Earth is a round ball by traveling on it, right? They say, if I do a whole round trip, the ball is round, right? They are very lucky. What if the conventional wisdom is right? The Earth is flat surface. They would not be able to come back until today to report it, right? The only reason they can report us because the Earth is not infinity, right? So infinity is something we try to avoid. Right? So basically, the thing here is, if you compare a flat plane and a spherical plane, right? One is a finite side, another one is infinite side. So we cannot use this to say which one is which. And also, in some way, I'm trying to avoid the straight line. Straight line, I'll say, have infinity in length in both directions, right? And yeah, I will cover that. Another thing is, when you look at the traditional definition of the Euclidean geometry, they try to define the geometry on a flat plane endless, right? But on physics, we don't do that. We just say, for a limited range, giving your measured accuracy, this is flat, right? So we don't say, basically, I only care about if it's local. This local area is a Euclidean geometry. And again, we have to test our abstraction, right? Suppose using our theory, we finally find out, using my theory, we find out the only testable thing on Euclidean geometry is distance, right? Now then we go back to say how the way we destroy a plane, right? Okay, the only thing is testable is the distance between 2 points. If our deformation of Euclidean geometry, we do not break this relation, then we cannot test it. We cannot test it. So in other words, when I fold a paper or bend the paper, it doesn't change any distance between any 2 points. In my standard, I cannot test it, right? But if I make a boundary or stretch it, I change the distance between some point, and I can test it. So that's why there's that's the reason behind why you say when the Gaussian curvature is 0, it's a Euclidean geometry is non-zero. It's not, right? Because one is a stretch, another one is not stretch. Okay, let's cover enough methodology. And here, I'm sure this one, I'm using formal mathematical language and just go through certain signs. So if I have an arrow, that means one condition leads to another condition, right? If I error on both sides, that means one condition leads to second condition leads to the first condition, because these two conditions are equivalent to each other. And there is this signal is like an E, but the reverse means exists in mathematics. If I put the exclamation mark at the end, we say exists the only case for this. Okay, so basically that is quantitative mathematics. And also I'm using set. The set, we can say there's a set contain nothing called empty set, right? We can have a set contain 2 points, say A and B, which call a set, right? We can also have a set defined, say I have a point P set by a certain function, right? These are all set information.
Excuse me, what does the exclamation point mean at the end of the
Unique.
Unique.
Exists and unique.
Unique.
Okay.
Exists unique. Okay.
Right. And we can also say an element is in or not in a set, right? Using this same symbol. And we can also, for two sets, if every element for one set equal to every other element from other set, we say these two sets are equal, right? And two sets can intersect, meaning they have a common element between them. Basically, I'm using this cap symbol. And if we have two sets and we combine them together, right, using this, what's it called, cap symbol, right, we say union. And there is a special union called orthogonal union. Basically, you have two sets, right, either has nothing in common, or in this case, at most 1 point in common, we'll combine them, right? I use the plus symbol. You will see in my talk. So let's examine the Euclidean axiom set. The first one says to draw a straight line from any point to any point. From today's understanding, we know what he's talking about, not a straight line, he's talking about a straight line segment, right? Straight line that connects the 2 points. Another thing is from our today's understanding, right? What's special for this? Because they are on the shortest path from A to B. Say, I have a connection from a straight line segment from A to B, right? They're on the shortest path. So from today, if I define it again, I'm saying I should define distance before the straight line segment, right? That's logical. And then the second one says to extend a finished straight line continuous into a straight line, right? Basically, what he said is you can make a straight line by extending existing straight line segment, right? That's also clear. Here, the word continuous is not clear, right? But we know, from now, we know the distance is a real number. The continuous means uncontinuous in the real number domain, right? In fact, you can continuous in the rational number domain. It's also continuous, right? But we know for knowledge, it's in the real domain, not in the rational number, right? So again, this one also continuous. If you want to specify clearly mathematically, you also need to use the concept of distance. And the third one is called to describe a circle with any center and distance, right? This can be saying, okay, I'm constructing a circle. Or you can also say it's actually an axiom about distance, right? Because you use circle to measure distance. And also, in this axiom, to describe a circle with any circle, it uses the word circle. It doesn't use the word ball, right? So it's hidden dimension information. I'm talking about 2 dimensions. I'm not talking about 3 dimensions. And the fourth one is that all angles are equal to one another, right? This one, first, is deviate from the 1 to 3. 1 to 3 is saying I can construct something. But this one is describe something, right? It's already an oddball.
Oh, excuse me, I forgot. How does Euclid define a right angle? I don't remember. How does he define?
He didn't define
a right angle.
He didn't define the right angle. Yeah. So
we have to go back to the Greek text.
Well, I have it somewhere. I mean, I have, but I don't remember right now.
So another thing is, what does it mean, right? What do you mean right angle? As you said. What do you mean two right angle can equal to each other? What equal means, right? none of them are clear. In fact, if you look at the literature, this axiom probably is seldom used, right, somewhere. And the last one is called parallel postulation. Parallel postulation is from where it started, is a controversial. If you look like the elements for Euclidean, the first four axioms listed at the very top, at the very beginning of the element. But the parallel postulation, basically, in Euclidean terms, said you have two parallel lines, and you have a third line cross each both of them, and the angle is equal, right? The crossing angle is equal. But Euclid himself doesn't say very clearly in the element that's at the front. Maybe in page 10 or something, he started to talk about it. And people think this is also axiom because it doesn't have any lead to it.
Go ahead, I'm sorry.
It doesn't have any lead into it. So basically, so people infer that Euclidean himself think this axiom should be redundant, it's not needed, okay?
I don't know what you mean by hiding it. I mean, he put it in made a list, and it was the fifth axiom
He
in
didn't
his
list
list.
as such.
I don't know what you mean by hiding it.
I think he lists I didn't read that element myself, but people claim that he had in some page later. Only the number 1, 2, 3, 4 he leaves in the beginning. So that's why people think maybe this is redundant. So in the historical, there is a lot of effort trying to prove the Euclidean to be right. So trying to prove that you can deduct the fifth parallel postulation from the first four, right? There's a lot of effort. In fact, this effort fails and give rise to the non-Euclidean geometry, right? Historically, right? Now, Euclidean geometry, as I said, is ancient Greek, so it needs some modernization. The first, there's several attempts, but the most famous one, maybe the founding of current geometry, is by David Hilbert, right? The great mathematician. And basically, he has before his axiom set, he had to have some undefined term. So the first sentence of his, by the way, this one I read is priming term. We think of these points, straight lines, and plane are these three concepts which not defined, having certain mutable relation, which we indicated by means of such word as are situated between parallel, congruent, and continuous. So these are all the non-defined terms, right? By the way, in my introduction to Hilbert axiom set, I will use a set language, but if the original one, not use set language at all. In fact, that's the one criticism I have with it, as you can see, because the set language make everything very simple, right? And also, in his axiom set, to my disappointment, it doesn't define distance, right? Only imply there is a distance in one of his axioms. So he also used the word continuous here. Notice that. And in fact, when we run through his axiom set, we will see that he had other undefined terms. And his axiom, instead of 5 axioms, right now he has 21 axioms into several groups. The first group called connectivity group, which contains 7 axioms. The second one called ordering group, which originally contained 5 axioms, but the one axiom is proven to be redundant. So it's prime minus 1 is 4 axioms. And there is a congruence group, which contains 6 axioms. And there is a parallel group containing 1 axiom, and there is a continuity group containing 2 axioms. We will go through each of these groups to see what they are. And it's kind of simple if I put it translate into set language. Also, a disclaimer here. I read his book called The Origin of Geometry, right? They have these axioms. And also I read another paper, another book by 2 Russian authors, and I compare these 2 axiom sets. They're different, quite beyond the translation difference. So I consult the wiki and give me a third set which is different from both of them. So basically my talk here is based on the wiki, and my paper is based on his original book, right? So don't quote me if I get something wrong here, okay? I don't know which one is correct at this moment. So let's look at the axioms for the incident group. Basically, it says, by the way, the convention here, if you use a capital letter, that means a point, right? If I have a point A and B and they are not the same point, there exists one, but only one straight line. Here, my convention here, AB saying that straight line contains point A and B. The star on each side, they will have an infinite point on each side, right? So that's just my convention. The second,
so you have to be able to distinguish points from lines already.
What?
You have to know the difference between a point and a line already, otherwise that doesn't tell you what
Yeah. So basically, you have a line and that. So here, it's the first thing I have to say is, from how the axiom set for Hilbert axiom set, it's, for example, for straight line, right? It did not give you definition, give you a few description. Okay. The second description of a straight line is there is a point. It's in the straight line, but that point is not A or B, right? The third one, it says there exists a point not in the straight line, at least one point. So when you look at these two axioms together, immediately you will think, maybe we should use set to define a line to avoid these trivial cases, right? Because when you do the set, the convention of what that means, right? And when you say there's a set, they probably means there are certain things in the set, something not in the set, unless it's an empty set, right? So this fourth axiom in this group says, if you have 2 points in an existing straight line code containing point A and B, and these 2 points does not equal to each other, right? And you can use this 2 points to define straight line, like use axiom 1. And the define the straight line CD.
Sorry, can you just read that? What it says? 4. I can't see.
It's on top of the other thing.
Just move the.
It's C and D.
Can we move that thing away? Yes.
Oh, thank you.
So if we have a point that's a number 4 here, the CD is on this straight line, right? They are different, 2 straight lines. You know, from the first axiom, you can define another straight line called CD, right? Contain CD. But this axiom say these 2 straight lines are the same straight line, they are same set, they're equal. Well, he did not use the word. My opinion, if the straight line is defined properly, this can be S0. The fifth one is, I say, if you have a straight line AB and then you have another point not in that straight line AB, right, C. And then you can decide a plane here, alpha, his convention, alpha, common convention, when you use a Greek letter, that means plane, right? Plane, there exists a plane which contains the point C and contain the straight line AB, right? Here, a little bit different because C is the point. We are, in my convention, every geometry is a set, right? So C is element for this plane alpha. AB is a subset of the plane alpha, right? So a little bit thing. So in this statement, what he says, right? He said plane, 2 dimension, straight line, 1 dimension. He is actually in bed assume dimensionality in this statement, right? And also, when he talk about plane, right, he's talking about a flat plane, right? This, as I said, right, this is also 2 dimension, right? I'm sure with a straight line and, with a straight line and point, and create that, right? He basically saying there's only one flat plane passing that straight line and that actual point, right? So he assuming the flatness. He is also assuming the uniqueness of the flatness. So basically this one is, we are discovering in his atom set there are hidden primitive terms, not only what he claimed. And the sixth one says, if I have 2 points, A and B, and this 2 point exist on a flat plane, right? We can say that the straight line defined by these 2 points are existing in that flat plane. The 7th S is if I have a point which exists on both a flat plane alpha and a flat plane beta, then there must be one straight line passing that point which belong to the intersection of these 2 flat planes, right? And here is something when you look at that, when you look at the axiom set, what he's trying to do is he's looking at this problem from 3 dimension. You know, he's looking at the 3 dimension. Here is a plane, here's another plane. And look at 3 dimension, look at the 2 dimension, right? So in this aspect, what this kind of geometry is called extinctive geometry. You look at something from higher dimension, right?
What kind of geometry is that?
EX is
Oh,
Intrinsic?
extrinsic, extrinsic, because you are looking at the 2 dimension from 3 dimension. Of course, in that case, you can tell, okay, this is flat, this is not. As we are looking here, but the 2 dimension geometry, in fact, the whole Euclidean geometry is intrinsic. That means you can characterize it, without from higher dimension. Let's just assume what 2 dimension people live in one of this plane. Can we tell whether this plane is folded or is flat, right? Is it Euclidean or not, right? In fact, that's real because Einstein says the 3 dimension world we are living in can be curved.
Can be what?
Can be curved. Can be
Oh, curved.
curved.
Sorry,
Can be
sorry,
curved. Can be. It's not
Yeah,
flat.
yeah.
Right? How would you come with that? We don't have an eye for 4 dimensions to look at 3 dimensions, how the thing is curved, right? We have to do it inside. It's called intrinsic geometry. So basically, so that's another thing I'm looking at is his.
Intrinsic, in other words, means with interpolation.
Yeah, so you basically do them. I will show you how you can do that in this talk, right? Basically, if you are basically you can imagine yourself to be a 2-dimensional people living in a 2-dimensional space. Can you tell what kind of space you are looking? What you are? Are you living in a ball, right? In fact, you can think about it in the history. We live on our Earth, right? Earth is a ball, right? At the beginning we think the Earth is flat. Then we know the Earth is a ball, right? That's the long before we go to the space and look at this. Oh, this is the Earth. That's a ball,
Well,
right?
if you're on the Earth and you lay out a triangle and measure it, the angles are going to add up to more than 180. So you'll know you're not on the
Yeah, that's one way. But
you'll know you're not on the
you're not on
Ocean
a.
navigation. That's the other.
Yeah. Also, you can go to, say, the other day I go to the beach. I go to the tower. I can see the sea is like a round to me. I don't know. Maybe that's a perception or not. But anyway, so basically what I'm trying to say here is, but Hilbert said, actually look at this problem from 3 dimensions. But actually, I will show you that the 2-dimension geometry, all the Euclidean geometry is intrinsic. You can decide what it is from inside. You don't have to look for a higher dimension. Now let's look at the other group. The other group, his original word, it says, between 2 different point A and B, right? There's straight line connect line. There must exist another point between A and B, right? If I translate to the normal jargon, they say, because you have 2 points, we can, the part which belongs to straight line is straight line segment. So I can say there exists at least 1 point belong to each straight line segment AB, right? And if it belongs to, if it becomes point A and B, it must be between the point B and A, right? So basically, I just translate to that. And also the second one says, exists a point, must exist point. Okay, I would reverse. The first one says, if there's a point between, another point between point A and B on a straight line, then it must be between B and A. The second one says, there exists at least 1 point between A and B on that straight line. Okay. So basically, so if we do some modern interpretation, that means if we define straight line as a set, that's semantic continuous set, right? That means you're guaranteed to have something inside. And okay, the second one, I don't know. The third one is a global requirement. What's this set? If you think about it, you have a loop, right? Or you have a straight line going forever, right? If you have a straight line going forever, you have a point A, a point B, right? And there is a point C between A and B, right? So that's okay. But if you have a loop, you have point A and B, you have a point C here. So C is between A and B.
Are you
In
talking
the
about a curve?
Yeah, let me
No.
make a drawing here. So it's
It says if this is the point on the line.
is there?
I need to see pictures, that's too complicated.
Okay, so I have one case here. I have point A, I have point B, I have point C, right? C is only between A and B, right? I have another case. I have a A, I have a B, I have a C, right? Okay, C is between A and B. B is C between C and A. Right?
Right, and A is between B and
yeah,
C.
it's
Okay.
basically Hilbert basically saying this case does not exist in Euclidean geometry. Well, I really don't care because this talking about something global, right? I don't care about the global, right? I only care about local. So I basically do not think. The fourth one is called partial axiom. Basically, what he said is you have a triangle, right? You have a straight line pass one edge of the triangle. It has to pass any of the other two edges, right? This is the axiom, but I think this actually, as you will see, we can use this to define what's the two-dimensional space. So yeah, so you basically let me make it on here. Here, you have a triangle here, right? If I have a straight line passing one edge of the triangle, it has to pass either this edge or this edge, right? But on the other hand, if you look at the three dimensions, what happened is you have a triangle here. I can have a line going this way, only pass one edge, don't pass any of the other two edges, right? So but this one, you can think it as an axiom, or you can think, I can turn it into a definition of the two dimensions, right? So I will show you how I do that. Then we talked to the Hilbert concurrent group. Concurrent group, he just say there's a mystery relation exists between two straight line segments, AB and A prime B prime. And this relation actually also applies for a straight line to itself. So what is it's not clear. Just say, here's the property. That's the problem is that, why you give me a lot of description without definition. It's not clear. And also, he basically say, if one first line is congruent to the second line, and second line is congruent to the third line, the first line is congruent to the third line, right?
Can you just read the first number one? If you read that, what does that say? It says if
It exists a relation, congruent relation. So this relation between straight line segment AB and A prime B prime, right? And this relation always apply to a straight line and itself.
Right.
The second one say this congruent relation is transformable, right? So I don't know the word. So first straight line segment is congruent to the second one comes to the third one, the transit, right? The third one is connection. If AB is congruent to A prime B prime, BC is congruent to P prime C prime, the AC is congruent to A prime, C prime. So basically, triangle relation, right? There's two, two, and the third one is.
Euclid, I mean, when he talks about congruence, does that mean if you place one figure over the other one, they coincide? Is that basically the way he explains it, or I don't remember?
It's more difficult than that because how you say on a plane surface, it's very obvious. You can move one thing from another and put on top of each other. But when you think of the curved surface and surface deformed, how you move one object from one place to another, right? They cannot, right? So that's why that's one thing we need to discuss. How you define this, and also.
Wasn't that problem already there with rulers? How do you move rulers from one point to another? yeah, because the ruler itself, as Einstein said, the ruler actually shrinks, actually bend, right? So
relativity.
So the fourth I'm saying this relation of congruence also apply to angles, right? So an angle can be congruent to another angle, always congruent to itself. Then this transient congruent relation also apply to angle. First angle can be congruent to second angle congruent to third angle, then first one congruent to third one, right? And the last one is the triangles stuff. So basically say AB is congruent to A prime B prime, BC congruent to B prime C prime, then the two angle
What do
congruent.
you mean congruent? You mean next to each other or the same?
No, it means
He just described congruent as an abstract term. That's the problem with
Oh,
it.
no wonder I'm confused.
it means it to be the same.
If you come a circle, then you do displace it in a direction it's the same circle.
Right. So basically, this congruent, in his axiom, he didn't define what congruent is. In the first sentence, we think this term to be applied to this. That's the problem I have with it. Without a proper definition, how would you describe it, right? And the next one is the axiom set is called the parallel group. So we come to the parallel postulation. As we all know, parallel postulation has many forms. The form Hilbert truth, he said, for any straight line at any point outside that straight line, right? There is the one, but only one straight line which passes that point and does not intersect with the existing straight line. Well, as an experimental physics, I have difficulty to test it, right? First, from each point, there are infinite number of lines passing by, right? How do I know which one does not come in? I could go infinity to say whether they interact or not, right? So it's basically make that infinity square problem, right? The first one I have to say, I have to go to infinity to say if the line connect with the interact with the existing line, and the second I have to do infinity line to find which one, right? As experimental physics, that's something I hate the most. And the second format, basically you say you have two parallel lines, they have certain property. First, you can make many for each point on one straight line. You can also make a line perpendicular to this straight line. And if this perpendicular line should always perpendicular to the second straight line, right? That's the first thing. Second thing, you can do many of these perpendicular lines between these two parallel lines, and the distance between these two parallel lines always the same. Well, that's very friendly for my measurement, right? I can make a line and make another line and say do a perpendicular relation with the first line to see if the second line is perpendicular, right? If it's not, then give me a hint. How I'm going to draw my next line? Maybe do a little bit other way until these two are of the perpendicular. Second one is if they are both perpendicular, then I can measure the distance, right? To look at the train, right? To see which my domain of interest. Do they shrink? Do they enlarge?
or do they have to train to meet each other or not, right? So that is a full motion, angular law. Right? So basically that is, the next one is a continuity group. The first one is axiom Archimedes. Basically said you have two straight lines, right? They have different thing, and you can always say you have a first straight line, second one. You can choose the second straight line, try to extend it, one time, two times, three times, and there always exists a number when you extend the second straight line. If it starts shorter than the first line, when you extend it multiple times, it will be longer than the second straight. I have actually a problem with that, as I said, right? On a plane surface, everything seems obvious. You can always do that, right? Extend that. But on a curved surface, when the distance measurement, like if you think about it, Einstein said, the ruler will bend, the ruler will shrink. How would you extend that, right? The meaning is not very clear, right? So, atom line completeness. Basically, the last one basically, in my opinion, kind of odd claim. Basically, he said all the previous axiom apply to everywhere, right? Without exception. Well, how much time do you see this kind of claim in mathematics? It's assumed, right? You don't claim something, it's applied to everyone, right? Basically, I infer what he said is, he said basically the space is boundless, right? There's no boundary, right? The boundary, basically the definition of boundary is something that's not apply, right? Secondly is uniform, right? Everything is the same. And third thing is a completeness. But I myself don't feel it's necessary because by convention, if you don't claim something, you will say this one apply to everyone, right? So there are some criticism of the two axiom set. By the way, because this two axiom set, if you teach geometry, that's the foundation of the current geometry teaching. First, it has a lot hidden saying like a distance, straight line, flat line, dimension, whatever.
Can I just ask, what is the status of Hilbert's axiom set? Are there high schools out there in the U.S. or China or elsewhere that use Hilbert instead of Euclid, or is it more sort of a niche thing?
I think I wouldn't say most high school would introduce Hilbert, obviously, right? But they always say that the Euclidean original one is not a mathematics strict. Okay. Right? They always introduce Euclidean, but most people that mention is not a mathematics strict. As we'll see, it is not. But if you go to college level, geometry, probably the first lesson will talk about Hilbert. Okay. So because they are common base, so let me say there are some problems. So the first one is, as I said, should have a distance, asking for distance first, right? Everything based on distance. The second one should have a use set for definition, as I also claim. And this same problem, angle measurement, that's how things started. Because when my daughter...
What does that mean? Should have used
Should
set?
have
You should have used set theory in the definition.
Right. The problem, because my daughter, when she learned geometry, said, hey, Daddy, how the angle is measured? Okay, I explained to her.
What did she ask you? How did angles work?
How you measure angle? I said, okay, yeah.
Oh,
You just, here's the angle, right? You just make a circle around the angle, and here's a curve lines, right? And you divide the curve with the diameter, you got the angle measurement, right? Because at that time I know in Euclidean geometry you cannot divide the angle arbitrarily, right? So even if you say all the right angle are equal, that means right angle should be unit to the measure, but you cannot divide it, right? You look at your protractor. You cannot get 10 degrees, right? You cannot divide the angle by 3/4. That's a classical thing we know, right? So
you mean with a straight edge and compass, you cannot trisect an angle?
you cannot divide the angle arbitrarily, right? So then you end up you measure the curve length and use that curve length. And the next question is how you measure the curve length.
And
Well,
what if the lines are a different distance?
What?
What if the lines are a different distance?
Right. And the second question is when you measure the, then I say, oh, something light up in me. How you calculate the curve length, the standard way to find the angular measurement times the diameter? What do we have here? We have circular definition, right? You're running in circle, right? You didn't define any of this, right? That's a problem, right? I look at the many books. There's no answer for that. So that's give me a hint. The Euclidean geometry, as it is today, is not that solid. And also, it assumes space to be stable, right? We are talking about a flat plane. So if the plane somewhere, maybe God's stretching it some way, right? You need to be able to do that. The final thing is, nowadays we're talking about the fractional dimension. Euclidean geometry is a 2-dimensional, 3-dimension. It doesn't have 2.5 dimension. But in real world, we have 2.5 dimensions somewhere, which I will show later. So Euclidean geometry is based on ruler and the protractor, right? So in 1930, there are somebody called Birkhoff axiom set. He's basically defined exactly Euclidean geometry based on these two measurements. Right? The first one, he said, for each straight line segment, it corresponds to a set. The set is a point running from 0 to line distance AB continuous in real domain, right? So basically, he already assumed assumption here. The second term, this one actually is very good because it answers you what the continuous means. Continuous means continuity in real domain. Well, in between means, right? Because between, if you have two different values, any two different value of real number, there are always some number in between, right? That's we know, right? That's why they are different, because that's called continuum and between. And basically, another thing he has is, for any two different points, you can always define a straight line with passing line. Well, I think, since you already defined the straight line, why not extend the straight line in the tradition of Euclid himself to define this, right? The third one is he also connect each angle with a degree, with a measurement. Basically, his units between 0 and 1. He basically said for each angle, there's a unique measurement with it, right? The last one, but my question for here is, you can have space has one fundamental measurement. You can define two fundamental measurements. In fact, if you can define one is a 2, that's something much better, right? You want to reduce this thing. And the last one, he basically says, if you have two triangle, right? And if they are corresponding lengths of each edge of the triangle are proportional, then all the angles are equal, right? So this basically says, using this, you can have all the property of Euclidean geometry. But the problem here is, this 4 axiom is kind of simple because it's not extensible, right? You cannot knock out one, get to another geometry. So what you want is, I guess what I want is, we want to have an axiom set, right? Which describes from, basically you put the limit to a smaller range, and probably, maybe at the last minute, you differentiate Euclidean geometry from non-Euclidean geometry, right? You want to have this as applicable, right? When you change the last axiom to something else, you can have maybe, say, specify the round, the spherical surface, something like that. So that's my goal. Let's see how I achieve that, right? Let's first look at some prerequisition for Euclidean geometry. I'm not a God. I cannot create something from nothing. So I have to start from something. So there's something undefined, but I only need one point. What is a point? Point is a location in space with no other property, right? That's the only thing I need. And I will use a set.
right? I have empty set, and in my opinion, all the geometric object is a set of points, right? And the space itself is a set of all points, right? That's my definition, and I will use the root number mathematics. And also I will use a limit. The limit I'm using is if I were 1, I can divide by half, divide by 1/4, 1/8. I keep on dividing that, right? The final result would be 0, right? And another thing is you add all this together, 1/2 plus 1/4 plus 1/8, you add them together, it's come to 1. That's the limit I'm talking about. I'm not using anything else fancy.
Sorry, when you say a set, I'm a bit confused what you mean by a geometric object, as in the set can contain geometric objects, or the geometric object is a set?
Geometry is a set.
Okay.
A geometry is a set of points.
Oh, okay. So there are a set of points.
Oh yeah.
So like a line is a set of points connected together?
Yeah, you will see. It's very interesting. You will see.
So just to be clear then, a set either has 0 elements or an infinite number of elements.
It could have a limited number of elements.
Oh, it can also have a finite.
Yeah, just a set. Not a set, nothing fancy.
Like this one here that contains 2 points. It's not on the screen, but it's
Yeah, it could be. Yeah.
So when you mean you're doing the dividing, are you just doing it, you're just doing square roots, or like?
This one,
Yeah.
1/2. You just divide everything, divide by 2 each time.
Well,
Oh, just by
I don't understand the 0 at the end, because you're never really going to get to 0. I mean, it's going to get smaller and smaller, but you'll never get to 0.
That was my next
If you go to
question.
infinity, it's go to 0, right?
That's the means by
It's the
limit.
limit.
Well,
What
So
all right.
there's also
I
a
usually
constraint to
usually
one to zero?
I usually remember not seeing the 0, just the dots. But okay.
Yeah. It could be 0,
Okay,
right?
alright.
What I'm trying to say, if you keep on this process, it goes to 0, right? I'm using
At
this.
infinity.
Yeah, infinity, right? So basically, that's all my prerequisition, right? I need a point.
Oh, okay, so those are your prerequisites, like those are
Yeah,
those
pre-recommend, right? So nothing else, right? The first thing I say, Euclidean space is stable. What I mean by that, if you look at what object Euclidean geometry can deal with, say a square, a triangle, a line, the first thing you know is you know the rule how to create them, right? How to draw them before right? You don't study anything you don't know how to draw them in Euclidean geometry. Each object is combined with a rule, right? So basically the concept here, all these objects are constructed, meaning they can create it by a set of deterministic and limited rules, right? Say, I want to do a square, right? I start from one point, draw one line, whatever dimension you specify, and draw another one here, draw another here. Right? That's all rule basis. In fact, the good thing about it is, if you apply the same rule again, you arrive with the same object again.
You didn't have length defined in your axiom, did you?
Later. That's the first one, right? So this one, say, the geometry is all simple. All can be constructed by rules, right? That's one thing. This also goes through the original constructive approach of the Euclidean, if you remember the first 3 axioms. This also says Euclidean space is stable, right? If I have a paper, I keep on stretching it, deform it. Even you apply the same rule, each time you are going to end up with different object, right? Because the thing is moving. And it also says the object itself is deterministic, right? A square, if you want to draw a square with certain specification, I'll give you that. And also it's a wide fraction dimension. Here's an example of fraction dimension. So you start with an equilateral triangle, right? You invert it, go on top of each other like this, right? Then you do it again for each existing equilateral triangle here. You keep on doing that. This is called Coach flag. And the Coach flag we know is has friction dimension is 2 point something. I forgot the exact number, 2.31, something. This is called fraction dimension, right? Euclidean geometry do not deal with this, so that's why I have limited, right? If I do an unlimited, then I have fraction dimension. I try to avoid that.
So by limited, you mean not infinite?
Not
Finite
infinite.
number of terms.
Right. So the second one is common. Euclidean is measurable. First, I define distance in a normal way. It's a real number between two numbers, right? If it is 0 between a number and itself, and it's a positive number.
So when you're saying if people reconstruct the same object, is that necessarily saying that it's not infinite because there's no way of measuring the same object you're talking about is infinite?
Yeah, that's another reason. But the main reason I try to avoid the fraction dimension. Okay, because you can have a simple rule, apply infinite number of times, and you end up with something called fraction dimension. In fact, normal object in 2 dimensions is also, for example, you look at the map of England, right? The problem is you go to coastline, you can see the wave, right? The coastline is by the wave. The smaller you look at the wave, the more complex the pattern is. So that means the coastline, shape of the coastline, the length depends on how long the ruler you are using. So that's called fraction dimension. But I try to avoid that, right? Euclidean geometry, we only deal with a simple object. We don't deal with complex object.
You deal with what?
Very complex object, like anything, like coastline, something like that. Maybe we can approximate, but we will not do that. So the distance is a measure of 2 points, right? So point measure from A to B is equal to B to A, right? It's larger than that. That's a normal distance definition. And also the distance, another definition is from 2 points, we measure distance, right? You get the third point, right? You measure distance between the third, say, AC and CB, and you add them together. It's always larger or equal to AB, right? That's your definition of distance, right? Abstract. I don't deal with the unit here. It's just the concept. You have to satisfy this to say it's a distance. So the second element, a distance exists between any 2 points, right? So if we do that, it's very great because suddenly make our space measurable. Make it measurable, then we are in job. We cannot measure it. As a physicist, I wash my hand. That's ours. That's not me. And if you think about it, if AB is a constant, right? AB is constant in a stable space. Because space itself is stable, right? You take 2 points, you make a measurement, you actually, in some way, you create a set, right? And use some rule to create the set. And this rule, because you do that every time, it's repeatable, so it's a constant.
Do you mean a real number constant?
Yeah, a real number constant. In fact, it's a good question. My other daughter asked, what kind of continuity? You can say the distance, as I said, the distance could be a rational number. It's still continuous, but it has to be real number because the later thing, right? So it's a real number. And also, from the definition of the distance, you say if 2 points, their distance is 0, that means they are the same point, right? So that's kind of quite easy. Okay, once I have measurement, I can define something called straight line.
Wait. So you just assumed you had these distances. You didn't say how to get these distances.
No, I didn't. Right, the actual distance, whether in inches, in meter, I don't really care. I only care all the distance measurement has to satisfy these 2 conditions. It's an abstract distance.
Right. So you don't tell me how I'm supposed to judge whether 2 line segments are congruent, because you didn't tell me that how I would measure this one and measure that one.
So you just picked
how would I discover if they were congruent?
Let me put it this way. Later in the slide, I will go into this subject. How you measure distance, because measure distance on the flat surface is a given. It's so easy. You just take a ruler and measure it.
If you know
But
what the ruler
on
is.
a curved surface, basically, let me put it this way. In distance here, has another term, generally called metric. Metric called, say, on a curved surface, right? the shortest path, the length of the shortest path between 2 points, we call matrix. And also, when we, on the flat surface, we call a straight line segment between 2 points, right? But on a curved surface, we use the term geodesic, right? The path of shortest path between them.
But I still need to know the difference between a ruler and a rubber band. I have to be able to distinguish them.
Right.
And do you tell us how to do that?
I'm saying that it has to be a constant. If you do a rubber band, each time, depending on how you stretch it, you may end up with different value, right? That's one thing. And second thing is, you are saying that when you measure the distance either A and B and B and A, right? They have to be the same value. Think about it. If you have curved ruler, right? It's not straight ruler. You measure the distance between two, right? And even say you measure this way, but when you measure reverse, it could be a different number.
But if you have two separate sets of points, how am I ever supposed to know if they're the same distance apart? How am I supposed to know if these 2 points are the same distance apart as those 2 points?
Yes, that is yeah, that's a little bit more difficult question, right? How can you? I can do measurement for these two distances that equal to each other. We don't know that, right? From the Einstein.
So you're just assuming that.
Just assuming that, right? For now, right? So I'm covering this, but I will come back to that.
So you pick a value for AB?
Huh?
You pick a value, like you pick a constant?
Yeah, just AB, just AB. Yeah. As long as you can assign a value between A and B, satisfy these two conditions, we say you come with a distance, maybe an inch, maybe meter, maybe something else. It doesn't matter, right? That's basically abstraction of all the distance in the world. Is that abstraction enough? I don't know. But it's not conventional. We can discuss later. So when we have the measurement of distance, now we can finally define a straight line. What it is, it's a little complicated, but let's look at the 2 parts. The first one, the second part, say, we know the distance between 2 points, right, between, say, we know before, this one here, right, AB is less or equal to AC plus CB, right? I just take the equal part, basically. Right, so that means I'm on the shortest distance, right? Anything not on this distance is not equal. Does not have it has a, it's not on this shortest distance. The second part of this is saying this set must contain a number of points, right? The number of points, this is a limit, but let's read it carefully what it is. Suppose n equal to 0, right? This set will contain the endpoint A and B, right? N equal to 1. This set contains the endpoint N and B, and the midpoint between A and B, right? N equal to 2 means this set contains the endpoint, the midpoint, and a midpoint between the midpoint and any of the endpoint. So basically, it says it has recursive midpoint, right? I have this set will contain all the recursive, the shortest distance, contain at least all the recursive midpoint, right? I say this is the straight line segment. Okay.
What do you mean by recursive?
Recursive means okay, I have to do. You can do it again and again, right?
Iterated, right? Iterated.
Iterated. You have 2 points. I find the midpoint, right? From the midpoint, I can find the midpoint between the midpoint between any of the ends. Right? From any of this existing midpoint, I can find another midpoint. I'm saying that as far as this is a minimum requirement for it to have straight line segments.
So sometimes you can have infinite processes, and sometimes you cannot. How are you deciding when you can use infinite processes?
Yeah, I will have an example coming up.
In this case, you use infinite processes.
Yeah.
Before you said, I thought you said before that you can't use it.
Yeah, this one, I will give you an example very soon. Okay, believe me. I thought about this. So once I have this definition, I can prove easily that this one, if you see, if the point C to AB, it must be BA, right? By this definition. And exists C in AB, that's also this. And also, another thing here is, I can prove my definition equivalent to this. Say, I have a point, all the point is on the short distance, and the point run in real number in distance, run continue from 0 to AB in real number. How you prove that? Okay, first, if I have this condition, I can create that recurrent midpoint, no problem, right? So, second is, if we assume this continuous distribution has a one gap in it, right? So we are saying suppose the gap from 0 to AG, right? Because I have to set the AB equal to AP plus PB, so the gap has to end between AB minus AG, right? So to satisfy that condition. So that means this one has no midpoint, right? So it cannot have, but I'm saying the straight line segment has to have midpoint, right? So it doesn't work. If I have a two gap, okay, you can have midpoint, but you cannot have the midpoint between the midpoint and endpoint, right? So by this kind of argument, you can say it can be a continuous distribution. It can have no gap. Well, this looks much beautiful than the original one, but why you need that? Let's answer your question. First, we also want to know what's the minimum condition for something to happen. That's always good to know. Second is when we do the experiment in the real case, right? We don't need the n to go to 0 or go to infinity. Let's give you an example. If you ever look at use a magnifying glass, look at the printout, any of these printout, right? You will see the straight line is not straight line, it's made from small dots, right? Suppose I want to draw 1 inch of straight line, right? I can have, say, let n go to 6. I can have 64 dots. My eye already said, oh, I didn't know, that's a straight line, maybe not perfect, right? So for the construction, 6 is n equal to 6, the decent number. If I go n equal to 8, if for 1 inch I use 256 point, no eye can tell the difference. Oh, that's a perfect straight line, right? So that's why, even definition I say that, but in reality, when you do the experiment, it doesn't go to infinity. By the way, even if it goes to infinity, the infinity has different order, right? This original one, the minimum requirement is much less than the other one, right? So from the physical point of view, I like this kind of thing, right? I can decide from my resolution, from my requirement, where the n stops. You know what I'm saying, right? So another thing we can prove from the set theory that if a straight line has a point in between called C, right? C between A, B, we can prove this equation that we can literally say is treat this straight line as an extension from AC to CB, right? And in fact, we can prove a straight line has a midpoint equal to say straight line has C in between A and B equal to straight line AC plus CB, on the set.
When the way you're using the term midpoint, you just mean a point between.
Yeah, a point, not the
Does
middle.
it have to be literally in the middle?
No,
Okay.
it's not. Let me retract, restate that. If you have a point between A and B on the line segment, right? This line segment can also be defined as an extension on the shortest path from the AC, from C to B, right? You start from AC, you extend from C to B, right? That's literally this equation means. And this equation also means you have, if you have straight line segment, you have any point in it, it can be viewed from set point, set concept. It is addition of AC plus CB.
So finding in the middle point is basically like considering a single line as two joined line of equal length.
Yes, the midpoint is.
It's just that.
This is not midpoint.
Yeah, and then so on and so forth.
And another thing you can prove, another interesting part is you have two line segments, right? AC and CB. And if you know the end AB equal to AC plus CB, so you can immediately prove that this relation reverse also true, right? So from this simple thing, you already have this so much property, right? And also Euclidean space, and we can also define something called round object. Here I don't say whether it's a ball or circle. It's true for every dimension, right? Because a round object is the set of points which has a constant distance from the center. Define that way. The round is a little interesting because you can say if some points inside or outside a round, right? It's a local object basically, or on the round. And for two round, center at A with radius RA and B with radius RB, what you can say that you can prove that if their center are so close compared to their radius, one is inside another one. And if their center distance are so far away compared to their radius, one is outside the others, right? So far with the second axiom, we already have so much property, right? Here's something. How about the relation between round object and the point? So what we are dealing with is this. So suppose I have a straight line has one end inside a round object, another end outside a round object. Then I can prove that there must exist one point which is on the round object. How do I prove that? Is I take this line, take the midpoint, right? Then look at the midpoint, whether it's inside or on or outside the round object. If it's on the round object, everything's proved, right? If it's outside in this case, right? I do it again, look at the red line, one side is inside, one side is outside. I keep on doing that, right? Either I directly find the point which is on the round, or until, as I said, this length go to 0. When it go to 0, that point become one point. That point cannot be inside and cannot be outside, so it has to be on the round. So that's basically how to prove it. All right, the question here is from here, visually, we only, line segment and the round only has one point as their intersection. But can I prove that? Well, I have a difficulty actually make mistake. Sometimes I thought I proved that, but then next day, maybe next week, I look at that again, I was wrong, right? There are some more fundamental problems with that, which I will come later. Then the next axiom says, Euclidean space is continuous or boundless. So the third axiom is, if I have two points, A and B, right? And I have a third distance AC. If AC is larger or equal to the distance between A and B, right? I can always control one, but only one straight line segment, AC, which passes the B, right? In the special case, if the AC equal to AB, that means I can always connect a straight line, right? So basically, this is a combination of between axiom 1 and axiom 2, right? So basically, when this one is larger, I'm extending it. When this one is equal, I'm connecting it, right? So this one tells us space continuity. Basically, what continuity means, you can also make a straight line segment with any 2 points, right? If you think about it, if I have a hole in this space, right, I cannot go across the hole, so it's not continuous. And also, this one implies, right, if you have 2 straight line segments, if they intersect at all, they only intersect at 1 point, right? So with this mentality, I can create something called ray, AB, we start on one end. So basically, I extend the AB on the shortest path, right? That's set. Basically tell you that, right? Because AP equals AB, that PP. And I can prove that if I have another point in this ray, right? And the ray is not, as far as the ray, that point is not A. This ray, AB, is always equal to AC using the set, which also makes sense, right? And also, I can define something called a straight line by extending on both sides using set theorem, right? And the first thing here is if I have point in AB, right, in the straight line segment AB, I can always, from the set, I can always break the straight line into two rays, right, join at C. You know, because the set gives us so much power of doing things when we define geometry algorithm as a set point. So basically using this definition, I can prove that every axiom in Hilbert axiom set has zero. For example, it's easy to say if A not equal to B exists AB, right? If A not equal to B, I can define a straight line segment and extend it. And I can also say AB equal to BA, right? That's very, you know, by looking at the equation immediately. And you can also prove very easily that if CD, a little bit tedious, but if CD is 2 points on the line AB, and C equal not to B, then the line defined by CD is the same as the line defined by AB. Just use the sets here. And you also can say exists a point in AB, right? And so another thing we can prove easily called triangle inequation. Basically this, right? Because when you see it's not in AB, just use set theorem. And another thing, we cannot prove, well, I don't think I care whether it's a straight line or a loop, right? But here something maybe replace that is if I can prove if C is not on straight line AB, then A is not on straight line BC and B is not on straight line AC. Right? This is, as you can see, it's always true, right? You can also check with the reality check. Okay. So continuous or boundless, right? So the third thing is, remember the relation between two circles, right? So before we only deal with A, B less than I and B. If it's equal, we say if the equal, then actually this is wrong. I need to correct it. If this one is equal, that means one is still inside another, but they have 1 point in common. Actually, this should be equal, right? Should not be less than equal. And this is also equal. This means these two circles, if their distance satisfies certain relation, one is outside, they are outside each other, but they have 1 point in common. This less than should be equal. This greater or equal should be equal. That's a mistake I will correct later. Now, let's come back to my old question. We are saying that if AB and equals round and straight line segment, and one end straight line segment inside round, the other side is outside round, I have difficulty to prove that there is only 1 point intersect. I know there is a point intersect, but I have difficulty. So as a physicist, you know, when I play with real fields, I always look at the real picture. The real picture is like this, right? I have C is outside I will run, say, from contain the EF, the point EF. And we can see that from this point in the Euclidean geometry, I just draw a picture. If I draw a circle, right, it's small enough, it's not going to touch the line. If I draw a little bigger, it touches the line just in one place, in D, right? And then I draw a little bigger, then it touch line E and F, a little bigger than A and B. What I observe here is the reason why this line only had 1 point touching the circle is because the distance between C and E increased monotonically with the distance between D and E. You got what I'm saying?
What is monotonic?
Well, monotonic means you just go in one way, always increase.
Oh.
There's no step, right? If the thing does not increase, it has a step, right? Then you are saying that at that distance you have multiple points. You know, when the line is inside, outside, it contains multiple points. Monotonic means it's always go up. In this case, strictly monotonically, right? It's strictly monotonic. This relation, because the relation between say CE and DE, right, is increased strictly monotonically. That's the reason.
You mean the same?
That means it's only increase, right? You have a curve always increase like that. You don't have flat plateau. If you have flat plateau, what happens is at that flat plateau, right? The straight line basically go on the curve for a while, then go up, right? So you have multiple points. So this is the reason. So that's the reason I could not prove it, because I missed this point. So
Well, I'm sorry, monotonic means, is it either increasing or staying the same, or
in this case it increases.
always
means
strictly
increasing.
leaves out the it's staying the same?
Exactly.
Oh, okay.
So is it changing on
Not
the
just
XY
increasing.
plane, or is it going just on the X plane straight?
The reason I'm talking about this first.
Yeah, we have it over there.
Yeah.
So you have it right here.
Okay. So I have a point here, right? This is called, say, I have a point here D, right? And here's a point E, right? I'm saying the distance CE, CD, and the DE. Monotonic means if this increase, this also increase.
Oh,
If this increase, this also increase.
Okay.
There's a one-to-one correspondence.
Gotcha.
And yeah, so that means that's the reason why when the line segment cross the circle, it has only one point, because it's always doing that,
Okay.
right? One-to-one correspondence. So that tell me the reason my math doesn't work is not because I'm bad at math, because I ignore certain things. In fact, you consider a lot of things. You look at this picture. Okay, you can see, say, if I find 2 points, A and B, on a round object, I connect them, create a chord. The chord always inside the round object. Say, in this case, it's a circle. Chord always inside the circle, right? It actually tells you something, right? Is that the general case? Well, when we look at the Euclidean geometry, it's a general case. But if we look at other surface, like a ball, what happens? If I'm here, right, I draw a circle here and do the connection. It's inside the circle, right? But if I say, suppose I'm at the pole, but my circle is so big, it's on the equator. When I connect 2 points on the equator, the line goes on the equator. You know what I'm saying, right? So the curve.
So it's a longer distance.
A longer distance.
Rather than
Now,
on
if my circle is larger than the equator, say I'm drawing from North Pole, right? The circle, I connect any 2 points on the equator, on this circle. Where is the shortest distance? Not inside this circle, but outside. You see what I mean? So basically, that says, you know, this one, you are measuring 2 things, right? If you are looking at, if you are looking at the chord that passes the center of the one, it's always true, right? It's always inside the circle by definition. But when you move away from the center, right, your environment changes, right? That may not happen. So I have axiom 4. So axiom 4 is you have 2 points on a circle and I connect them to create a line segment. That line segment is inside around, right? So I already go through the spherical surface. And because of that, right, this is true, I can prove one thing. Is for any point not on a straight line, right? Always exists only one point on the straight line which has the shortest distance to that point, right? Basically, you can draw a circle like this, CD, right? You draw a circle that has only one straight line and everything else is outside. That means CD is the shortest distance, right? So I call the point D is a it's a distance between this point and the straight line, right? And also, I call the point D as the tangent point between C and the straight line. I just use this nomenclature. So
did you give a constructible means of finding D?
What?
Did you give a constructible means to find point D?
The D is the D is called the tangent point between the C and the straight line AB, right? We just didn't say exists one. How to construct one, how to find that, that's another story. Because on different surfaces, you have different strategies to find it, right? And the Euclidean place is most easy, right? Which I will show you how to do that. But I'm just saying there exists a point, right? Not 2 points, 1 point has this property, and it has also all the other properties is monotonic. That means this, right? So the monotonic also means it has no local minimum. It only has a global minimum. So what I mean by that is, suppose this one I'm proving by contradiction. Suppose I have a global minimum in D, right? I have another local minimum in E, right, between this, and I have a point F. Because between two local minimum, there must be a global minimum, local maximum called F, right? So if I measure the distance between that point C and the line, I must have some curve like that, right? Then what I can do is I can make a circle using C as circle, CE as a distance, right? So this one would cross at least 1 point of this straight line at G. So the curve between G, F, E is outside this one. So that's not possible, right? So that means, so this is just a way to prove that it's monotonic, has only one global minimum, nothing else. And also we can extend this idea to two straight lines AB and CD to be perpendicular to each other. The reason for that is we can prove mathematically if I have a line AB and another point CD and the D is their tangent point, and every point on the CD straight line has D as a tangent point. That's the first part. Second part is for the same condition. Every point on AB has the tangent point of D. So these two prove that we can extend this to two straight lines perpendicular in general case, not only for Euclidean. Now let's come to the dimension, right? So far we were talking about this. What I talk about is true for all the dimensions, right? How we define dimension? You see every straight line is the same in all the dimensions. 1 dimension is a straight line. It's a dimensionless property. But the round object has different environment, right? It's a circle in 2 dimensions, a ball in 3 dimensions. And also you can look, when you have 2 circles, when they intersect at all, they also intersect at 2 points, 1 point or 2 points, right? But you have 2 balls. Oh, I don't have another ball. Say, here's one ball, here's another ball. When they intersect, they intersect at a circle, right? So using this, okay. Before I go that, I need to ahead myself. Using this, we basically can define dimension. And here, we just describe what happened in 2 dimensions, but we haven't defined dimension itself. So how we define dimension? The dimension is this. If I have a line like this, right? I have a point on one side, right? And if I have another point on the other side, right? So if I make a connection, they always meet the line, right? So basically, for this relation, I say point CD is on the different side of the line AB, right? I use a symbol there, right? If I have a point C on this side, I can define all the space. Say, suppose that the C is the bottom. I can define the space on the other side of the line by saying that space is characterized for all the points who, when you connect with me, passes the street, has any connection, an intersection with the line AB, right? So I can define a space. So the 2-dimensional space is defined as the line itself and a point on this side, which defines the opposite side, and the point on the other side defines this side. So the axiom 5 says, when you have 2 circles, when you have the case of 2 circles intersect with each other, they intersect 2 points. This 2 points is on the different side of line AB, right? And use this, you can define the 2 dimensions. You actually determine the 2-dimensional space. Another thing is, if I take a flat plane, twist it, and connect it.
Sorry, excuse me, it's 10 to 9. We will have time for asking questions. We will?
Yeah.
Asking questions? It's 10 to 9.
Guan, is there any particular time that you need to stop or what?
Not really.
Oh, okay. All right.
So basically, if I flip that and then connect that, right, what we got is called Rubus ring, right? The interesting part is, I can apply this locally to the Rubus ring. So, but when the circle is big enough, this relation breaks. So that tells me that the Rubus ring is 2-dimensional locally, but not globally, right? And for the same token, if I'm doing the paper, I cannot stretch it. We can also say, in many cases, we can have Euclidean space to be locally, but not globally, right? So that's why I'm saying, maybe when we discuss the global Euclidean space, doesn't make sense, right? That's okay. And here we discuss something called triangle, right? ABC, 3 points, right? This also defines something called triangle. Dimension also, I will hurry up. Say we have 2 straight lines which they intersect, right? It's a form an angle. So how we measure the angle? Well, I already choose that our traditional one. So basically what I did here is, we still do a circle from where it is crossed, but we measure the distance between BC, right? I take a square, divide by the radius of the thing, right? Radius thing, which I call the angle measurement distance, right? So this whole thing I call angle measure distance ratio. The good thing here about, if you're talking about a ray, right? The ray, we call the 0 angle. This value equal to 0. If you are talking about a straight line, right? At the point at, correspond to your pi angle, this one is a value of 1. And also another good thing, you have 2 angles, right? If one, say the D is the inside AC and the AB, right? So you can prove that angle distance ratio of the ACAB is larger than DAB. In other words, angle distance ratio is proportional to the angle.
So, in other words, you can define all the rest of the geometry.
Yes.
All right.
There is a good property you will see with that. We can also say there is a supplement angle, which is a BAE is a supplement to BAC, right? They're opposite of EAC equal opposite to this. And a special case, if the two things, we already say two lines can perpendicular to each other, right? In this case, we say each angle is, every angle is a right angle, and the special case for angle distance ratio using this measurement because right ratio. Let's do that, right? Now, the next one is the plane space is smooth and flat. What's that mean? That's our thing, but we have to define it mathematically. So the next one is we know the angle distance ratio between 0 and 1. So when we divide them into equally in half, what's the angle distance ratio should be? It should be 1/2. What I'm saying, the angle distance ratio for right ratio or right ratio are 1/2, regardless how you measure what's the radius. Angle distance ratio used to measure it. It has a good property. It's a perfect divider, right? And also it says smooth. Let's say, suppose I have a cone here, right? We know the tip of the cone is a sharp point, right? But if you think about it, I'm doing a straight line passing this, doing another straight line, basically divide that, you will see immediately that angle distance ratio is less than 1/2, right? But you measure other places, it's still 1/2. So basically, let's say this is a singular point. So that's why it's not smooth, right? The smooth, just say angle right ratio somehow should be a smooth function of your location, not a singular point. The second one is a flat. When we talk about flat, we cannot talk about this paper by itself. We have to compare with other surface. Here, I'm looking at the surface. So suppose I have a ring, right? I can calculate angle distance, the right ratio from the outside or from inside. From the outside, we know it has a Gaussian ratio to be positive. Basically, it's a ball-like surface. The inside is what's it called, a hyperbolic surface. Basically, you have a paper, right? You try to stretch it one way, right, on this direction. You stretch it in another way, in another direction, right? Suppose this is rubber. If we do this stretch, the center here is called hyperbolic. That's a negative Gaussian curvature. So here, the interesting part here is when we look at the right ratio has a positive Gaussian curvature, we see the thing decrease and decrease with your measured distance. When you do it on the negative Gaussian curvature, you see the thing increases, right? So by measuring the angle distribution, you can tell exactly at which point, whether it's in Euclidean, which is 1/2, or whether it is in another neighborhood. Another thing is, when it's 1/2, there's something interesting. You can say, suppose, for argument's sake, suppose I create two perpendicular lines here, right? They cross at point A, right? Then I measure distance AO, BO, CO, DO to be all distance 1, right? And because this is a right angle, so we immediately know the length of AC is square root 2, right? But the length of AB is 2. So that means the angle ACB, CBD, BDA, DAC, they all right angles, right? You have a shape with, all right angles all equal in F. What do you create? It is a square. You can create square any way you want because any length, any direction, you can do that. From square, you can create a triangle, right? Say, in this case, I put the two square side by side, right? They have the same length. ABC, EDC, they all right angles. So that means ADE is a straight line. So I'm creating a rectangular of ratio 1:2 for height to length, right? I can put any number of this anyway. I can create a triangle of any proportion right? But so here's the consequence. Is if I can create I can create a rectangular that way. That means pari postulation already proved. If I put a lot of this triangle together like that, right? They have a straight line. They all have the same distance, no matter what, right? I already proved that the postulation. So yeah. So here. So this shows that Euclidean, his hinge is correct, right? The only reason is, if you have the right angle, you have a way to quantify it. You say all the right angle are equal to each other. In my case, I quantify it. You don't need that parallel postulation, right? Though there's more consequence for that. So basically, we can try to tile the whole space with squares, right? What we are creating is a Marian grid, right? We can use a Marian grid, to compare any part from any part, right? To see, for example, I compare these two triangles. So that means because of that, the Euclidean space is homogeneous. Everywhere it's the same, unlike maybe some shape, right? Like here, right? The tip of the point is different from everyone else. It's isometric. The measurement from everywhere is the same. And isotropic, all the direction is the same because I can create the triangle, square any way I want, and reflect it. So basically, the thing here is, suppose I have a grid, right? I have a BC, B prime, C prime, and for every point A prime, I can only find another point A double prime, which is on the perpendicular at the same distance, right? These two reflect each other. And another thing is similar. Similar means, I can shrink because of the size, right? It doesn't matter. I can shrink this. For example, in this case, if I shrink ABC, right? By scale, I just shrink
So you'll still maintain the same proportion.
You still maintain the same. I just shrink it by my grid, by value, right? I can go on A prime, C prime. So as a comparison, if I look at the most similar surface than the plane, right? The ball, right? The ball you can still put any. You can still use a triangle or polygon to tile it, to cover it, right?
Yeah, that's how 3D modeling works.
But the problem here is you can only do with a selected size. You cannot do with any size. So on a 2D spherical surface, it has all the property, but it's not similar because you cannot shrink the size. So I will try to conclude this as soon as possible. I know someone is the time. So here is an issue for one. Now let's talk about object in Euclidean geometry pretty quickly. Here's the idea for repeatable. When you think about repeatable object, when you think of how to create any object, say I want to draw a square. I first find where I want to draw a point, right? Then I want to know on which direction I want to draw it. So when we construct an object, if you can construct this object, follow this rule, you can repeat it. You first have the first rule. First rule start with a starting point, a starting rate, right? Then you have the rest of the rule, which only refers to each other and the first rule, but otherwise do not refer to any other location or direction information, except the first rule and the individual state. When you draw a square, the starting point, my first edge, right? That's the direction, and then I have the length. Draw a perpendicular only relate to the starting point, right? Then I draw the second one, which relates to the second edge, something like that. If all your created objects obey this rule, I call it a repeatable object, right? And also, I have a concept called property. A property is a true statement of all geometry objects. And we can categorize the property in different way. You can say if a property is only related to the starting point, we call it the position-related property. If it's only related to the starting rate, right, we call it orientation-related property, right? Another thing is when I draw this triangle, suppose I know the two lines, I draw the circle. I can draw either this side of my starting ray or the other side of the starting ray, right? When I draw on the other side of the starting ray, I reflect each other, right? So I call, if you want me to draw a triangle, I can draw this one. If you want to draw it here, I can draw it on the same side. Same side I call repeated. And if I draw on the other side, I call it reflected. And as I said, the thing is similar. So when you ask me to draw a triangle, right, I can scale the distance all by a constant, right? And that constant called scale. So basically the distance related is, if you're only different by the scale, that's called distance related, it's a scale. And it's finally like a angle measurement, right? It's a ratio related. So basically, you can have addition property like an area. Area is the square of the distance related. So basically, the idea here is how you construct the object determines its property. Namely, here, if you draw the thing, if you say somebody wants you to reproduce a triangle, if you reproduce a triangle on the same, using the same scale and on the same side of starting ray, what you got is called repeated congruent. Repeated congruent means it may differ from the position-related property, differ from orientation-related property, but they have same side-related property, distance-related property, everything else, right? If on the other hand, when you try to construct a triangle on the same scale but different side, what you got is reflected congruence, right? Basically, your position-related, orientation-related, side-related may be different, but everything else is the same, right? You can repeat it on different scale and have this thing. So this is basically what the end of this thing. So basically, I'm defining a congruence, define different type of congruence, define different type of similarity. Summary as a protection. So basically, my axiom set compared to this one is a test string. Everything can be tested. It is simpler than Hilbert axiom set, and it's also progressive. Unlike each atom is follow other, limit your scope until the last one limit you to Euclidean. Here I'm going to jump something since it's too late. I actually find a general solution when you think about the general surface, right? How you find the distance between the shortest path between these two, right? The traditional way is user functional. It's too complex to me. I basically find some way to do it, right? Instead, but I'm not going into detail. So far we talked a lot of things. We know what's a flat, but the one problem we haven't solved is a flat unique, right? Can you find a unique? It's a flat. You think about it. For 3 points, you can find a lot of surface which go through that, but only one of them is a flat surface, right? And also, if you look at another surface like a ball, right, a spherical surface, it has a parameter like how big it is. But the flat plane has nothing, right? So my last axiom actually says all the right ratios are 1/2, right? That's how I come to the conclusion of Euclidean geometry. My question is, if I relax this axiom to all the right ratios are constant, can I prove that constant is 1/2, right? If I can prove that constant 1/2, that means the flat surface is unique, right? So that's the unanswered question. Great. So I have acknowledged a few acknowledgement, and my middle school teacher who teach me how to do the alternative thing, and my college instruction, two of them, asked me to concentrate on the concept, the idea, rather than skills, because their advice to me is, you are good enough, right? All the skill, all the knowledge you can read from maybe some dictionary, maybe special dictionary. All the skill, I think you can do it yourself. The concept, you teach it. And my PhD advisor, when I do the PhD, I go with another professor for 3 years. I generate 6 papers, 5 of them first author. But then I feel bored. I go to this professor. He's doing a complete new idea, new area he doesn't know himself. And for the first 1.5 years, the only requirement he gave me is, okay, you need to discuss your reading every week, once before. And that is quite, because he will question right and left, right? I had to come up with idea, discuss it. And also another author who find some fatal mistake in my past approach here. And math teacher journal, I write this paper and sent to 20+ journal, all rejected immediately without going into the review process. And math teacher's journal is good enough to accept it and review it, because I'm nobody in this field. And also your enrollment, I think if you feel interest, look into my paper, see if you can find more mistake or improvement, acknowledge the economy, and also, because this idea, the concept, rather than because I complain a lot about U.S. Education indoctrinated, maybe in your ability, you should try to promote more things about concept, about thinking. I was keeping my other several other efforts. So let's stop here. So any questions?
Yeah, I would like to make a couple of points. The first point, alright, so the first point is that I can show, I thought of it, I can show how set theory cannot be applied to the description of infinite lines. So let's say you have a point, right?
Mm-hmm.
What is the rest? Empty space, right?
Mm-hmm.
A point, that's only what to consider, right? With this.
Yeah.
Everything else is an empty space. Now, in set theory, every set, it's a theorem, every set contains the empty set. Every set, whether it's non-empty or empty, every set contains the empty set. Now, the empty set
is a subset of every set.
Yeah, but anyway, every set contains, besides other ones possible, every set contains the empty set. Every set, that's a theorem.
It's subset.
No,
because
it's not a concept. The empty set, zero and cross, right? That empty set is included, but the theorem is included in every set.
Yeah.
Set ABC has to include the empty set too. So it's ABC, comma, that snack, right? Now every set contains the empty set. Now, what is the empty set? The empty set is, you can have an empty point, that's also an empty set. You can have 10 empty points, that's also the same empty set. You can have infinitely many points, that's still that very empty set. Now, if you have a line, and you put the empty set into that set, according to the description of the set theory, right? Of infinite, now fine, infinite. Now, you have an infinite line, you put an empty set, that empty set breaks the line in two. That's not already the line. That's it, that's a contradiction. This means, I just thought of it just now. Anyway, that means that you cannot use description of set theory in the modern sense because of that theory. You cannot use that set theory for description of infinite lines. No problem for finite lines, yeah. So you have a finite line and everything else is the empty set. But infinite lines, you cannot use set theory description for you.
Nothing what it means.
I think that's a contradiction because the
Yeah.
real numbers are constructed from sets, and they
Okay.
represent an infinite line. And the empty
Zero,
set doesn't break them.
No, the empty set. I mean,
Yeah. But the real numbers are constructed from sets.
Yeah.
Right?
Yeah.
The real numbers form an infinite line. And
real
they're not
numbers-
broken by
Yeah.
the real numbers form a continuous infinite line,
Yeah.
and they're constructed from sets.
Yeah.
They're not broken by the empty set.
They're not what?
They're not broken by the empty set. I don't think that works.
Oh, real line.
Yeah.
Oh, infinite. Oh,
It's
I see.
constructed. It's infinite. It's constructed from sets. I don't think. I think you'd need to write that down and see where it works.
No, but it considers the number 0, right? Real line. So I mean,
Yeah, why not you write me an email?
you can put that 0 anywhere you want. That's
Write
really
him.
Write me an email. I will look into that. But in
Okay.
fact,
All right, no problem. Cool. All right.
Yeah, in fact,
And another point is that it's a very short point. Another point is that what we consider as lines, points, whatever, figures, objects, distances, angles, whatever concepts, all those things are inseparable from our everyday experience, and besides that everyday experience, we cannot tell whether there's actually, in actuality, in reality, does exist as a real line or not. One can argue this way. My argument is that you can consider first initial consideration. You can consider first initially, let's say, only two objects exist in the universe, right? A and B. Nothing else exists, just those two objects. That's consideration. Just that's that. You have only 2 points in the whole universe. Nothing else exists but just those 2 points, A and B, whatever, right? Now, what is between those 2 objects? I'm sorry, not a point, objects. A and B. What is between them? What is between them? Only they exist, nothing else. What is between them? Nothing. But if there is nothing, if there is nothing between them, what separates them? Nothing. So they are inseparable, and they are one and the whole thing. Logical, right? It's perfect.
No, yeah, you need to formulate your argument in the set, then I will look into that.
In a set?
Yeah.
We don't know what a set is one of the
Yeah,
objects.
so
A set is the object, you consider set. Only
yeah,
2 objects.
let me put this way.
So the object A is the set.
Let me put this way. Suppose I am a very
No,
concrete
plane
term.
is already an object. You have only 2 objects in the universe, nothing else exists. What separates them? Nothing. So they're the whole thing.
The distance can go
You have a distance that's included in one of the 2 objects.
right. The distance depends how you
No, you
define.
don't have a distance there. You have only 2 objects that exist in the universe, and nothing but that.
I think you
An
need to write this
axioms.
framework down and we can circulate it to the group.
Axiom 2 states there has to be a distance.
Okay, let me finish that. I don't see any contradiction here because this is the initial consideration. Consider 2 separate objects. Separate.
Okay.
Consider only 2 objects that exist in the universe. If you want to say space will be one of the 2 objects.
Okay.
So only those 2 objects exist in the universe. What separates them? Nothing, so they're inseparable. So it's perfect. There is nothing that separates them. They're inseparable. They're one the whole thing. Now, you can consider a gazillion things.
Look, I think you
Let me
need
finish.
to write this down. And if you post this,
I want to make a point.
We'll all
Let
receive
me
it.
finish. Sorry, let me finish. Now, you can consider gazillion to a gazillion's power of all things in the universe, right? What separates them? Nothing. They're all inseparable, just like those 2 things. They're all inseparable. That means that everything is only one thing. So that's the argument, and that shows if the argument is correct, of course. Now, if that argument is correct, that shows that everything in the universe is the same thing, inseparable from any other thing. So we, in our daily experience, we can say, this is my hat, this is my jacket, this is her jacket. We separate those things, right? So we separate those things, and in everyday experience, we perceive them as separate, and we perceive them as separate objects, and we can say that a line is not the same as a point, because we differentiate those objects and anything else that is entailed in our daily life experience. But in actuality, in real actual reality, based on this argument, here's the argument described. In actuality, everything is only one thing, inseparable. Now by myself, I a little bit extend this argument. Now consider this situation. So we have that everything that is one thing. Just for simplification, let me finish. Consider it as a ball. Consider it as a ball. You have a ball, and there is nothing besides just that one inseparable single thing. That's everything. If you consider nothing besides it, so you can picture it this way: the ball and everything else is nothing, just that ball. Now, the argument is this that I extended. If you consider that something and nothing, there must be a border between them, right? But if nothing is by definition nothing, then it's no thing, then it doesn't have a border. That means that's contradiction. I mean that means that if you have the border, that nothing becomes something because it will have a border with everything, right? That means that nothing does not exist because it will have a border if it would exist. That's it. Everything is just one thing without nothing. Nothing does not exist by definition too, right? In our understanding. Nothing does not exist. And everything has no border with any nothing. Everything is one thing and there's no nothing. Everything is just one thing. It's call it infinite, call it without end, call it whatever. That's it. That's the reality according to this argument.
Why not you write me a detailed message and then I try to answer that? I couldn't follow it. But can we give other people a chance to ask questions?
Presentation.
What about this? So, do you imagine this as a basis for teaching geometry, for example, in high school or something? Have you talked to math teachers about, so from what I could tell, you don't need that many prerequisites as a student, as a learner, but you do need some comfort with sort of the language of sets, for example. Have you sort of talked to math teachers about whether this can be taught to a 15-year-old?
Yes, I think so, because I already taught on island. Selected kids called creative, institution of creative, something like that.
What age were they?
I think 14, because they already know the set theory. They already know everything. You know, the 1 equal to 1/2 plus 1/4.
Yeah.
They already know this. My daughter attended that school, but I realized in that school, for the enrichment, they still do not teach you how to think. They teach you a lot of advanced topic, small fitting, right? So that's why it's my concern. Because geometry itself, the good thing is very logical. Second thing is very isolated, right? It does not contain. I can play with geometry without any number, right? With not any real number, real calculation, but everything is relation. So I talk to them. I'm trying to. That's one thing I think if you think is interesting. If you have nephew, niece, maybe you read the paper and discuss with them, right? Because that thing I think is really like in this country is the math logic teaching. So that's why I say your involvement is required.
What do you think about the Common Core math curriculum?
Well, the Common Core, let me put it this way. I think first it's a good thing. I can tell you a joke. I don't know whether it's a real thing or not. When I first go to Swinburne, I have to be a teaching assistant, right? I have a roommate who is also physics major, who is also teaching assistant. And he basically teaches Math 101. And he said at that time, in 1990s, right, the math is really bad in the country. Nobody paid attention to it. And one of the problem is, basically in the college, 101, the first semester they have to do the high school math. And one of the problem is, they select multiple selection. This is a trigonometry problem. And you say, select the trigonometry form, which can be simplified further. And a few students, he's talking about 300 student course. Quite a few students select sine x divided by n can be simplified further. And TA was stunned. How could you simplify sine x divided by n? It turns out the kids come to the board, they cancel the n from the top from the bottom. Sine x divided by n become number 6. That's how it does. So
that's
funny.
They say which one can simplify. So Common Core, at least on that end, give some requirement to the teacher. You have to teach kids, otherwise your kids will fall miserable in Common Core, right? That's the good part. It has a minimal.
It's so demoralizing. Like my sister can't even teach her 13-year-old kid.
But the bad part is I don't know whether it's politically correct or not. They try to push every kid into the Common Core, the same path, right? You think about it. On the same class, there may be some art-related kids, art-oriented kids, some literary-oriented kids, some STEM-oriented kids, right? For the STEM-oriented kids, you probably want to put a different paths, like taught them at least two-year geometry, right, rather than 1 year, right? The Common Core force everybody go through the same paths, right? That's not a correct answer. So it's good and bad, I would say.
How long do you think? You said in the beginning that you in your school in China you learned like it took you 5-6 years to master all this. So how long does it take to master this material if you start like in high school or junior high?
I think the thing here is when we taught the math, we basically, at that time, China worked 6 days a week. So we have class 2-hour class every 2 days. And basically, we have something in parallel, right? When in the middle school, right, we have 2 years of plain Euclidean geometry. At the same time, we have in parallel 1 year of the analytical geometry, right? When we go to the high school, we have 1 year of solid Euclidean geometry.
You mean the primitives, like a pyramid?
Yeah, this kind of thing, right? So we basically prove each step geometry is for proof. For the we have in parallel analytical geometry.
What's analytical geometry?
So X, Y, Z, X, Y, Z
are
the
based 3 dimensions.
So it's
Analysis applied to geometry.
Analysis applied to geometry, and also the trigonometry applied to geometry. Something. So we have something in parallel. But I have to say, in China now, they lost this approach, because this approach, the kids, they concentrate a lot on the basic concept, on the thinking, right? And also we are required to solve one problem multiple ways. But in China right now, it's like in the United States, they push too much things to the point that some good schools start to teach a graduate level math course to high school tier. You think about it, in this country, I think it's absurd. You have to go to AP to go to best college. But if you are really good in AP, you should go to graduate school. You should skip the college. You know my argument, right?
So you're saying that they push advanced material too fast?
Yeah, too fast. This true.
No wonder I had a hard time with math in high school.
So basically, the U.S. Because my kids go through U.S. and I can compare with China. At the beginning, elementary school to middle school, everything's super slow, right? When this 12 years, 13 years kids, you are teaching them 1 times 2 plus 3 times 4. You do this kind of thing. But when you go to high school, everything suddenly like a waterfall, right? Everything crammed. That's wrong. I mean, but I have to say, in China at my time, the progress is more reasonable, right? You expect kids to be, to a certain level. We have hard elementary school schedule, but there are something good or bad. I don't know if it's good or bad. In this country, basically no child left behind, right? The schedule is based on the last kid in the class, right? Basically, everything.
You mean the curriculum?
In the curriculum
until
middle school.
Curriculum is based
You know,
on the slowest learning kids.
Yeah, but in the China, there's another system. The system is kind of evil because, they give different kids different level of education. If you are good, you pass, you're good, then you are in top 1-2 class, which give you something different. You are normal, you can have class 3 and 4, which give you normal level. When you are not very good, you are 5 and 6. The good part is for the good kids, you compete with your peers, you see how the understanding. But the bad thing is for the people left behind, they lost interest, right, very soon. So it's hard to say, but I would say, at least in this country, you should look at the kids, differentiate, common core, if you can have a common basic requirement plus differentiated requirement for different subjects. Like maybe, the kid, I want to be a mathematician, right? Maybe you should give them 3-year or 2-year plain Euclidean geometry, right? Try to pressure again. Because I think I don't know, I think you are a math major, but I think my understanding is math research is different from all the math Olympiad, this kind of thing, right? One is skill, and you can train. The other one is give you thinking, your idea, this kind of thing.
I was going to really quickly say, have you read the book Mindset by Carolyn Dweck?
No.
So she articulates exactly what you're talking about the growth versus the fixed mindset. And the growth mindset is the kid doesn't quite finish the puzzle and then feels great about having tried and passed his level. And then the other one is just, checking off the boxes. Anyway, that's all. Yeah.
Should we, one more? Or,
Yeah.
One more. Couple.
I want to make a quick comment. I was born in the Soviet Union. What you described in the Chinese system, I think it's very similar to the a lot of Chinese system was taken out of the Soviets. My son studied at Stuyvesant High and was a Dutch student there. And at Stuyvesant, they used the Russian translation of the Russian geometry book by Isidorov and Kolmogorov to the understand. So over there, at Stuyvesant, the education is very rigorous. And I just want to mention that we started studying geometry on a daily basis from the 5th grade.
Yeah.
And it's like planimetry, stereometry, trigonometry. So from the 5th grade to the 10th grade, because the Russian school used to be just 10 years, was a daily study of the geometry. Every problem in the geometry, we were supposed to start from the basic axioms.
Yes.
Of Euclidean Sales, or we used to call Thales as in Greek. So, starting from the basic axioms, we would have to step by step to prove lemmas and theorems.
Yes.
And it was a problem in geometry was like an essay. It was like many pages, like step, next step.
Yeah. Sometimes in China is that too. We don't go through the axiom, but if you know some of the theorem, we are cool. But the thing here is, in China, we don't use a theorem unless we prove it, right, in the class, right? And unless we fully understand it. And as you said, I think that's one problem in this country. All the exams are multi-choice. It's easy on the teacher, but bad for student, right? Because if you say, like you said, we may not be an essay, but it's quite long, maybe 10 steps, right?
We never had multiple choice, but all exams were oral. Oral exams, so you have 15 or 20 minutes to prepare. To solve the problem. Then you talk to the professor or to a teacher. And he judges how you think. So that was a job. But it was never multiple. Never. Not in a single function.
Okay, so I guess. you very much.